Which is trying to say something.
Can you hear me? Test. Konnichiwa. Arigato. Arasmasu. Yep.
Which is trying to say something.
Can you hear me? Test. Konnichiwa. Arigato. Arasmasu.
Yes, sure.
I can also put close. Yes.
Which is trying to say something.
Can you hear me? Test. Konnichiwa. Arigato. Arasmasu.
Yes, sure.
I can also put close. Yes.
The venue. Can you try to say something again?
1, 2, 3. Test. 1, 2, 3.
Let's wait a little bit for the because I think it may be a compliment. Gone. Yeah, so I think it's the problem with the so now it's okay.
How about the venue? The microphone for the venue?
Yeah, it's working.
No problem?
Yeah. It goes through the YouTube, so it's the Zoom should work.
Before you start talk, I need to introduce you to the audience, and it's going to be in English and Japanese. So
Okay. If you feel like you can just cut parts, I don't mind about it being so long.
Also, Professor Ogata also give greeting.
Okay.
For the official event of the venue.
Wonderful.
Thank you very much.
Do you want me to be in a specific place?
I think it's fine. You can just
Anyone.
walk around. Yes.
And I should keep my mask.
For speaking, I'm not actually sure about that, but maybe it's fine to.
I'm okay with keeping the mask with this one.
Okay.
Okay. Hi, Alex.
Hey, how are you?
Good. You? Good. Nice to see you again.
Nice to see you. You're in Japan?
Yeah.
Hope the jet lag is getting better.
Yeah. It's actually traveling east, west. I usually am okay. Traveling back is gonna be hard.
Oh, I see.
Well,
Look forward to you talking.
thanks.
I'm not sure where
I expect a lot of questions now.
Okay. I'll do my best.
Yeah.
And concerns. Concerns and problems. Yeah.
Okay. So see this. It's now in front of the screen.
In front of the screen.
The camera should be in front of you.
Okay. Will people be able to see the screen?
Just
Okay. Yeah, I was more concerned about the people in this room, in the middle too much. I cannot switch. Okay. Yeah, I probably.
on the other side would be fine. And this is the clicker you would like to use.
Wonderful. May I also turn it a little bit?
Yes, sorry.
May I also turn it a little bit?
Sure. Yeah, definitely. I will start the time when you. Stand on the other side.
Hello everyone, let's get started with his talk. I'd like to welcome everyone and thank everyone for coming. I'm Roberto Calandra, assistant professor at the Waseda University, and we are pleased to welcome Dr. Roberto Calandra from Meta AI. And he worked on robotics and tactile sensing. He received his PhD from TU Darmstadt, and he was a postdoc at the UC Berkeley. He's a research scientist at Meta AI and doing great research projects with his colleagues, I think. And I'd like to have a really interesting talk today. Also, we could have his talk as an official event of Waseda University from a great support from our staff. So on behalf of Waseda University, we would like to have Professor Tetsuya to give his short greeting. After that, let's move on to Dr. Calandra's talk.
Okay, thank you for the welcome to this meeting, lecture. Anyways, thank you for joining us. So I'm Tetsuya, now another leader of the ICT robotics unit of Top Global University, Waseda University. Also, this event is supported by the AI Robotics Institute, Waseda University, and also the global program, doctor program of embodiment informatics. I always forget the English name, sorry. But actually, it's a really good opportunity to discuss about, and especially focus on the tactile sensing, very important functions in robot systems. And I also have the continue on this kind of collaboration, future collaboration between Waseda and Meta. Yes. Yeah. Thank you. Thank you very much.
Thank you, Professor Otta. So, yeah, please start your talk, Roberto.
Thank you very much. It's a great honor to be here today, and I'd like to thank again Professor Ogata and Professor Mabashi for hosting me. So today I'm going to talk about a topic I've been very interested for the last few years, and the talk of today will be perceiving, understanding, and interacting through touch. The slides are available online if at any point you know in the future you want to go through them. And I'll start by first telling you what I'm generally interested in. In the last few years, we have seen fairly impressive advancement in machine learning and specifically reinforcement learning. And we've seen things like AlphaGo that are really capable of learning how to control or to play games. But most of these applications that we've seen are fairly limited to environments which are very structured, which are fully observable, which are simulated environments where it's possible to achieve the equivalent of hundreds or millions of years of human experience in a very short amount of time. And some of the fundamental questions I'm interested in answering is how can we scale reinforcement learning, machine learning to more complex and structured domain where there might be sparse data, there might be a limited amount of data, and we don't have hundreds of years of time to learn how to do things. And some of these fields are things like logistics and decision making, finance, biological sciences, and above all of them, robotics is the field that I'm sort of more interested in. I've been working in this for many years, and this is where I'll be focusing most of the things I'll be telling you today about. And the question of why robots? Why should we be interested in actually developing robots and mechanical systems that can help us? I really believe that there are many fields into our society where having help of robots would be beneficial. Starting from industrial automation, where I would personally like to see all kids that still work in coal mines and make jackets for us be replaced by robots. I think that there is no need anymore in the 21st century for this type of low-skilled manual labor. Things like disaster relief, where we've seen with Fukushima and with hurricanes and all of this, that robots can actually be extremely useful to reach in time, be fast there. And exploration. We already have robots on Mars. We already have extensively robots that explore the depths of our oceans. And this is going to stay because it's simply too hard for humans to go in this environment, which are dangerous and not friendly. And finally, medicine and elder care. With an aging population in many of the sort of societies in the world, we do want to use small robots in order to improve the medical system and to generally improve the quality of life of elder people. And if we look at what's the state of the art, this is a video from the DARPA challenge that you might be already know from 2015. These were some of the best team in robotics in the world, working for 3 years with, in some cases, team of hundreds of people on trying to have robots doing relatively simple tasks like walking through some paths, manipulating objects, opening door. And what we can see here is the fact that fundamentally these robots are stupid. Fundamentally, these robots fail in a way that no humans, not even a 3-year-old kid, would fail. No kids would ever do something like this. And part of the problem is really the fact that these robots at the time were hard-coded, and they do not have the capability of being able to adapt to new environment or changing condition. And do not have the possibility of being intelligent qualitatively in the same way that a human is. So the question is, what are we missing? How do we get from these, stupid robots to something that is actually useful in a real world environment that can be used safely in our houses and can meaningfully interact with humans, again, in a safe way? And of course, this is a very complicated question. And I personally believe that there is a whole spectrum of key challenges that needs to be solved, all the way from hardware design down to software and control. But fundamentally, I believe that machine learning is going to play a really important role in order to be able to achieve this. And some of the questions that we've been working and focusing over the last few years include things like multimodal sensing, optimized hardware design, and quick adaptation to new tasks. And for all of these scientific questions, we have lines of research that have been focusing, for example, on model-based reinforcement learning, morphological adaptation. And specifically today, I'll be talking mostly about touch sensing. This is going to be the main topic of my, of the rest of the talk. So, why touch? Touch is fundamentally a crucial sensor modality in both humans and robots. From an evolutionary point of view, touch is the first sense that evolved in animals when we were still small amoebas, monocellular organism, and we had cilia to just move along and bump into other monocellular organism. And this means that it's very deeply inside our brain. You can be born without vision, you can be born blind, but you cannot be born without sense of touch. And we very often use touch, barely even realizing it, how much we rely on it, how important it is. And part of why it's so important is because unlike vision, unlike audio, allow us to sense directly contact forces. And in the moment we want to interact with the world, we need to be able to measure and balance these contact forces if we want to be able to achieve accurate and meaningful interactions with the world. And in humans, this is very, we know that from physiology that this is the case, that people use touch extensively. And here is a video from Ronald Johansson, where they would first ask people to solve very simple tasks like lighting a match, and then they would anesthetize their sense of touch. And suddenly something that is so simple and intuitive for people would become extremely hard and challenging to achieve. And this is because we do actually use touch, although we don't fully appreciate how much we actually do that. And touch sensing, one question is, why don't we have touch sensing in all of the robots nowadays? Touch sensing is a field that has been progressing for the last 15 years. What is pulling us back from actually having robots that use touch? And there are many different answers to these questions. It's of course a very complex sort of answer. Part of this is the fact that touch sensing require, it's a very hard technical sort of problem on its own. But part of what we believe is also crucial here is the fact that touch is an interdisciplinary field, which really goes all the way from, from hardware design of sensors to then the processing. And then once we are able to make sense of touch, we want to put it inside a control loop, and how do we integrate it? And finally, how do we use this type of control loop into a particular application? And having this whole vertical integration is something that is extremely hard from a scientific perspective, because any lab that wants to tackle this problem needs to have an extreme level of expertise across multiple levels. And this is very rare. And moreover, a fundamental problem of touch sensing from a historical perspective is the lack of reusability. There are hundreds or thousands of tactile sensors that have been developed throughout the last 40 years, but most of them remain at the stage of prototypes, where somebody built it, used it for a PhD thesis, and then it just simply, it's forgotten in history. And part of this is just the fact that it's hard to share sort of this advancement with other researchers. And this, of course, leads to people reinventing the wheel over and over again, because there is no way of building on top of what's already existing. And as a result, entrance bar for new researcher in this field is extremely high, because in most cases, if you are interested in having robot touch in your robot, you first need to be able to build it. And this is, a whole field and a whole challenge of learning how to build tactile sensors. So some of the questions that we've been interested in trying to answer over the last few years is, how can we lower the entrance bar for researchers in tactile sensing? How can we improve reproducibility? And how we can overall accelerate research by enabling this type of block reusability, where somebody somewhere builds something which is cool, and the other researchers can build on top of it and use it to progress faster. And the answer to this, not surprisingly, is that we believe that standardization is crucial in order to be able to do this. And really, as a community, we should be thinking a lot about creation of ecosystems of tools that people can use, can share, and can be built upon. And in the rest of the talk, I'll be presenting one ecosystem that we've been developing at MetaAI exactly for doing this, for accelerating research in the field of tactile sensing. So one thing that I want you to sort of look through my eyes is really to think, how are we framing and how are we thinking about tactile sensing? And I want to give you a historical comparison. At the end of the 1900s, the wide availability for the first time of telephones at scale really enabled people to be able to record audio, transfer it, and then replay it on the other side of the world. And this not only led to, of course, a plethora of very interesting applications, but also led from a scientific point of view to the creation of a field of computational science dedicated to understanding audio as a sensor modality. So how can we record audio better? How can we digitize audio? How can we transfer it? And more recently, this has directly resulted in fields of machine learning applied to audio, fields like natural language processing, which have been extremely and are extremely successful and allow us to do things that were unthinkable just a few decades ago. And in the 90s, a similar fast progress happened with vision, with the introduction of digital sensors for the first time in the 90s at scale. We saw how people are now able, all of us, we have cameras in our pockets, into our cell phones, and we can all
use it and make use of all the advancement that we have also from computational science, because together with the wide availability of hardware also came a science dedicated to the computational, studying the computational foundations of vision, and of course the machine learning side of it, which is computer vision, which is another extremely successful field. And what I'm here proposing and suggesting is the fact that now in the 90s, we are at the verge of having, for the first time in history, tactile sensing availability at scale. We have technologies which are reliable enough, we have technologies which are cheap enough, and with having this sort of hardware availability, it will naturally come the fact that we not only will create new applications for it, but we will also have to create a new science, a new field of computational science dedicated to touch, with the goal of essentially understanding what's the nature of touch, how to digitize it, how to transfer it, and ultimately how to replay it back on the other side of the world. And in order to essentially achieve this goal of being able to digitize touch, we've been thinking about four main pillars into our research and into our work. And these four pillars are hardware, touch processing, simulation, and benchmarking dataset. And here is the sort of the fundamental idea is, how do we make touch sensing useful? What are the key components that we are still missing? And both as a scientific community and more in general for applications. And in addition to this, today I will also be briefly talking about applications that we had of touch and how we've been trying to help the community to essentially accelerate research and be successful. So let's talk about hardware. As you probably know, and as already mentioned, there are hundreds, thousands of tactile sensors that have been built over the last few decades, but really very few of them have gone beyond the stage of being purely prototype. Alex here, I'm extremely pleased to say that he actually managed to go through that barrier, and you went into commercial products, which I think it's amazing. But very few people have actually been able to do this successfully in a way which is also financially viable. And when we talk about tactile sensing, there are many important factors that sort of constrain the type of sensors that we want to or are able to use. And just to get an idea, some of these important factors are, of course, availability. So how easy is for me to buy one, to build one. Cost. It's is this going to be cheap and inexpensive, or is this going to be extremely expensive so that I cannot buy more than one or two? Form factor. Am I interested in having something like a fingertip, or am I interested in having something like artificial skin that I can place all over the kinematic structure of my body? Capabilities. What am I actually sensing? Am I measuring the human finger, the human skin has many different type of receptors that capture different aspects of touch, from the geometry to the forces to the temperature. What are our digital sensors measuring, and with which capabilities, with which resolution, with which frequencies? And finally, reliability. Unlike cameras, touch is an intrinsically active sense, where in order to be able to sense the world, we actually need to create contact. And this results in an extremely high amount of wear and tear compared to other type of sensors. And the human skin is amazing because even if we cut ourselves, we have self-healing capabilities, so the finger will just grow back after a few days. But we don't yet have this type of technologies in tactile sensing. So we need to make sure that the sensors that we build are sufficiently robust to withstand hundreds of thousands or millions of interactions with the world that we want to probe. And the type of technology that we've been sort of adopting and we've been using at Meta AI over the last few years is the so-called vision-based tactile sensing technology.
The basic idea is fairly simple. Is the fact that we have some type of elastomer, typically a silicon, and then we have structured LED below this elastomer, which are projecting light onto it. And then we have a camera, typically a normal camera that you can buy off the shelf, which is essentially pointing at the elastomer and will record essentially the colors that are the light that is being reflected. And whenever an object is now deforming the elastomer, this will create changes in color hues and shadows of how the light is projected back into the camera. And this will essentially be recorded by the camera, therefore, providing us data of what's the geometry and the forces that are being applied onto the elastomer. And as a small contribution to this field of vision-based tactile sensors, in 2020, we designed and open sourced the first mass-producible compact vision-based tactile sensor, which we call Digit. And Digit was really designed with the idea that we wanted to have a sensor which is relatively small compared to other vision-based tactile sensors, but most importantly, that is cheap to design and reliable, cheap to manufacture and reliable. And with the goal of trying to democratize tactile sensing technology for as many people, as many labs around the world as possible. And the idea was also to make it simple to use. So for example, for connecting is a very standard USB port so that anybody can just plug it in without having to worry about drivers or strange protocols. And these are the type of images that you would get out of a Digit sensor. So this is, for example, a piece of Velcro, and you can see the individual teeth that are being sensed by the sensor. Here is some piece of electronic. And overall, we have a spatial resolution which can go down to about 15 to 20 micron, which is fairly remarkable. And because we don't have any moving part, like in capacitive or resistive technologies, the reliability of this type of sensor is pretty high. And even if the silicon break, we can just replace it without having to replace any part of the electronics, which is very inexpensive and fast. Now, comparing the Digit to the leading tactile sensor commercial available at the time, which is the Biotech. The Biotech has about 29 taxels, while Digit has 300,000. So quite a few more. And the Biotech is sold for about $15,000, while the components for building a Digit are actually $15. So we can see that this is quite a lot, sensing quite a lot more from the world, while being a lot cheaper. And moreover, Digit is open source. So anybody can just go to this website, digit.ml, can download the schematics, can 3D print it at home, order the electronics online, and it's relatively easy to assemble one manufacturable. Now, over the last couple of years, we've seen over 20 universities replicating it in-house. But most importantly, last year, we partnered with Jetset, who is a startup in Boston, so that they could actually commercialize it. And the really cool thing is that in the over the last year, they sold over 1,000 of them, which makes it probably the most widespread tactile sensor in robotics, simply because it's so cheap that anybody or most university can actually afford to buy one. And very recently, just a couple of weeks ago, also Digit was selected to be part of the new Mitsubishi Electric race ecosystem. So many companies are now either evaluating or starting to really try to use Digit into their ecosystem, which of course makes us happy, because the more people use it, the more this helps the field hopefully to progress faster. So besides hardware, the next pillar is simulation. Simulation is a fundamental tool in the toolbox of every scientist, not only in robotics and machine learning, but really anywhere. And the reason is because with simulation, we can very quickly prototype, debug, and in some cases, benchmark progress in a way that sometimes is not possible in the physical world, which can be more expensive or slower to evaluate. And one of the problems with traditional simulators is that integrating tactile sensing makes them slower, because the more contact points we are trying to evaluate, the more the computation becomes harder. And most rigid body simulators that are available in robotics will basically break around 1,000 contact points. They will become so much slower than real time that it doesn't really make sense to use them anymore. And so, as I already mentioned, vision-based tactile sensors like Digit can have hundreds of thousands of contact points. So simulating something like Digit is actually a technological problem because it's not possible with standard simulators. So what we did in 2020 and published in 2022 was to open source and release a vision-based tactile sensing simulator, which we call Tactile. And Tactile is capable of simulating vision-based tactile sensors at hundreds of hertz. And the nice part about it is that it can be integrated in principle with any physics simulation of your liking. So if you use Bldg, if you use Bldg or Isaac Newton, doesn't really matter. As long as you can extract forces out of your simulator and geometries, you can integrate it with Tactile, you can integrate it with different sensor configuration files, and you can simulate vision-based tactile sensors very, very fast. Now, Tactile does not directly compute the physics because it doesn't solve the question of physics. So you will still have to rely on having an accurate physics simulator if this is what you care. But everything concerned with the rendering and with the optical property, Tactile is the right tool for doing this, and it's extremely good at actually doing this. So here, for example, there are some images of out of a simulator and the corresponding images for the same object onto a real sensor. And qualitatively, they are actually fairly realistic. They are very, very close to what a real sensor would provide. And even more, Tactile can actually be used for sim-to-real transfer, which is something that people in machine learning are using more and more. And we demonstrate with experiments that by doing sim-to-real, we can directly train a model in simulation and use it in the real world. Or even more, we can train something in simulation, add a very small amount of data from the real world, and perform better than training a model only on large data sets into the real world, which is really cool because it makes it easier, again, to debug and design models that actually work as fast as possible. So once we have a real hardware, once we have a simulator that can simulate this hardware, the next step is touch processing. How do we make sense of the output that our sensor will provide? How do we interpret this higher dimensional data and transform it into something that can be used for control or perception? And here the emphasis of what we have been sort of thinking and trying to do is to really create this new science dedicated to touch processing to make sense of touch. And there is an extremely limited literature over the past decades of work that try to understand this fundamental nature of touch from a computational point of view. But there are really important questions that needs to be answered in the coming decades. Questions like, what are the features that are important for touch? Can we learn generalizable features in the same way that people in computer vision already know how to do things like ImageNet and all these corners, edges? Also, what are the important structures from touch that we can exploit? We know that touch is intrinsically a local sense. We know that touch is intrinsically an active sense where spatial structure is relevant, temporal structure is relevant. How does this influence the type of model that we are able to train and use in order to make the learning faster?
And finally, how do we quantify touch from a mechanical and sort of perceptual points of view? So, and even here, as a very small step forward, we open sourced the first machine learning library dedicated to touch processing, which we call PyTouch. And the idea is that with PyTouch, you are able to take, in theory, any sensor, or in our case, digit. You can connect it with your computer. You can download PyTouch, and together with downloading this infrastructure, you are then able to also download pre-trained models that comes with different capabilities. So, for example, being able to detect touch, being able to predict sleep. And the nice part is really that we've been trying to make this as seamless as possible so that even people that are not an expert in tactile sensing or in machine learning can essentially use these models very, very easily and without much technical expertise necessary. And the way that we are thinking about it is that we want to make PyTouch really a framework where different models can be evaluated, different sensors can be compared, a little bit like OpenCV is for computer vision. A framework that everybody use, that everybody can contribute, but also can in theory use by downloading things, pre-trained models, and so on. And we are we've already been adopted by, for example, by Gelset for some of their product, and we are talking with more companies and university to try to adopt PyTouch as widely as possible into the field. And these are some of the nice features, but really the one that I think is most important is the fact that PyTouch allows touch as a service where non-expert people can really download pre-trained model and use them very, very easily. And this is, for example, a 3-line code for using a touch detector onto a digit, where essentially you just define that you have a sensor, you define that you want to detect touch. This line automatically downloads from internet the corresponding pre-trained model for the particular sensor that you specified, and you can now predict if there is touch or not happening. Now, this is, of course, interesting both from an application point of view, but it's even more interesting from a scientific community point of view, because really it starts moving toward the side of how do we compare model easily? How do we enable people to benchmark things easily? And one of the cool experiments that we did with PyTouch is to train models across different types of vision-based tactile sensors. And we showed that by training in this multi-sensor way, we can learn features that are better performing than training on a single specific sensor, which sort of already point to the sort of hints that there might be generalizable features of touchiness in the same way that we have features that are generalizable in computer vision, and we really should be investigating more and more what these features are and how can we learn them efficiently. And more recently, just a couple of weeks ago, we put on arXiv a paper where we show that we can learn joint vision and tactile sensing features in a task agnostic manner through self-supervision. And then we can, after we learn this feature, we can actually apply them to different tasks, both perceptual and control tasks. And this feature perform better, again, than feature trained only on that specific task, which, again, it's a very interesting concept that really tells us about the fact that it should be possible to learn generalizable features. So the fourth pillar is benchmark and dataset. Benchmark and dataset are the heart of a healthy scientific community. And so far, benchmark have been something that is very much lacking in the tactile sensing community.
And part of this is because of the lack of standardization in terms of hardware and simulators. And only recently, only now that we start having sort of accurate simulators and standardized hardware, we really can start thinking about what are the benchmarks that as a community we want to create and we want to start adopting. And this is, of course, not something that I don't believe that this is something that should be imposed by somebody. I think that should be something that is done by agreement in the widest possible set of researchers. We should probably have this discussion, Alex. And it's really important, I believe, that we actually do this as a community, because this is, for example, something that computer vision have been extremely successful at, defining benchmark, going after them and showing progress that, from 10% in MNIST, now it's solved, and then they create a new benchmark and you go after it and you really show that there is a path, there is movement in the field. And the dual of benchmarks are dataset. There are very, very few publicly available datasets in tactile sensing. And I think that, again, as a community, we need to invest more into this. We need to also give proper credit to people that spend the time and effort to collect large-scale dataset onto hardware, because it's painful, it's a lengthy process, but it's really, really important. And as a very small step toward this idea of starting to explore large-scale dataset, together with our Tactile simulator, we designed a very simple sort of benchmark/dataset for grasp stability. The idea is that you have a single object, you have a manipulator that grasps this object 1,000,000 times in different places, and then from the tactile readings, you want to predict whether this grasp is going to be stable or not after you lift your hand up. And the interesting part is that the dataset we could collect in a few hours was 2 orders of magnitude larger than the largest publicly available dataset that was actually collected in hardware. And being able to have large dataset start to enable us to investigate machine learning models at a scale which was not possible before, using only data that we have in hardware. And this is, I believe, going to be very important to really push more and more larger dataset that, as we know, can be very important for machine learning models that we use nowadays. So finally, I believe that applications of tactile sensing will be very widespread. I believe that there are really a lot of applications that could benefit from the presence of tactile sensors, but I will now discuss some of my favorite ones, or the one that I would like to see more and more. And some of the key applications here are things like prosthesis, where it's very obvious that if we can actually provide people back the sense of touch, whether it's for grasping or for locomotion, we will have very positive impact into our societies. Another field is the metaverse, and I will be spending one word on this next slide. E-commerce, where in the same way that we can have nowadays with our phone visual queries, where we take a picture of an object and say, hey, buy me something that looks like this. One day we will be able to do tactile queries, where with our sensor we touch a sweater and say, hey, buy me something that is with the same material or the same softness or the same thread that is being used in this sweater. And finally, robotics, which of course is what is closer to my heart. And I believe that within robotics, there are many subfields, starting from agricultural robotics to medical robotics, industrial robotics, of course. And the use of tactile sensors, I believe that will be very important to be able to solve things like manipulation, because we need to be able to accurately sense and control forces. Now, if you think about touch in sort of from a social and emotional sense, we all know that touch is a really important sense. There is nothing in our life like being able to touch or hug the loved ones. There is nothing that emotionally strikes us and and make us happy as much. And this is because, again, touch is a very old sense, and it's very deep into our brain, but also open very interesting possibilities, because if we are able to now sense the world, sense touch, process it and transfer it and be able to reproduce it, we are now able to feel the gap, the distance, and really feel people that are far away also from almost a physical perspective. And of course, touch sensing here can play a really important role, especially in these two first blocks of how do we sense the world, how do we digitize objects, how do we digitize interactions, social interactions, and process them before we play it back. And this is a paper that we wrote a few years ago, now almost a decade ago, which I think it sort of very gently goes in this direction, where the idea was that we had a robot with tactile sensors in the fingertip, and then we were having haptics gloves, with the vibration motors to play back this tactile sensing feeling. And this was integrated into a first-person teleoperation framework, where people could look through the eyes of our Oculus Rift, which were the eyes of the robot. By moving the head, could control the eyes and the neck of the icon. Then we had a Kinect that was tracking the kinematic pose of the operator and played it back into a robot. And finally, we had this glove that was controlling the hand and sending back tactile feedback to the operator. And having this tactile feedback was actually very important in order to achieve good body schema for the operator as fast as possible. Otherwise, they would need a lot of training in order to be able to do even simple tasks like grasping. And finally, we've been exploring many different shapes of tactile sensing in the context of robot learning, in the context of being able to use learning and robotic applications. And some of these tasks go all the way from predicting grasp stability, learning how to regrasp objects, identifying objects from touch. So if imagine that you have your hand inside a drawer in the dark, can you determine what you're touching without actually being able to see the object? And tactile exploration. And very recently, we had two papers on 3D reconstruction from vision and touch, both in a passive way and in an active manner by deciding where to sample next. And this is a good paper because it really shows this sort of complementary nature of vision and touch, where vision gives us global information about the scene, but then touch is very local. But in the moment when we decide to touch something, it gives us extremely rich, extremely high resolution information of this very tiny small patch. And how to integrate this global data and very localized data is actually a very interesting problem. And recently at IOS, just a few days ago, we presented a sort of funny paper where we learn in simulation how to play piano. Given a score, we learn how to modulate better the timing and the sound and the force applied to the piano in order to play a score. And to do this, we use tactile sensors in simulation and the use of reinforcement learning and modularity so that we can learn how to basically follow the score accurately and at the right time. And finally, I believe that touch sensing is going to be extremely important for fine manipulation. In this work, we were interested in having glass marbles between two fingers and being able to roll it to the desired position. And this is actually a really difficult task for a robot, because at the same time, you need to be able to apply enough force so that the marble doesn't fall between the finger. But you should also not apply too much, otherwise you're going to squeeze the marbles sort of being shoot out of the finger. And in order to do this task, we use model-based reinforcement learning, where we essentially take raw images from the tactile sensor, we encode it into some latent space with information bottleneck. And then we use it to learn a power dynamics model, which given the current images of the touch and candidate action, we are going to predict how the next state would be looking like if we would actually apply this action. And once you have a power dynamics model, you can use it in conjunction with traditional control algorithms like MPC, and basically choose which actions you want to use to go from A to B. And this actually worked very well. So finally, all of these robotics applications that we have nowadays in manipulation are still very, very far away from the dexterity and the capability of a human hand. And there are really, I believe personally that touch is going to play a really important role in order to be able to do this. And there are hints, including some work from Professor Ogata, that touch is actually helping us to achieve better performance in many tasks. But at the same time, it's not obvious yet, especially for people that are not in robotics, that this is the case. And just a few weeks ago, we had, this is a video. Yes, should be playing. Okay. We essentially demonstrated, to my great surprise, that it's actually possible to learn how to manipulate dozens of objects into the real world through using sim-to-real transfer without the use of neither vision nor touch. All of these policies are learned exclusively through the use of plioperceptive information about joint position velocities. And this actually worked extremely well. We originally just wanted to make a baseline to show that touch works better. And turns out that this is actually its own paper, because we can do things that are fairly impressive. And we just train in simulation, move it to the real hardware, and it worked very, very smoothly. So to conclude, we, in the direction of really building this community of tactile sensing, we have created a Slack channel, which anybody can join at touchsensing.org. This is completely free. It's not connected in Meta in any way. And we already have several hundreds people that are sort of part of this community. If you work in this field, I recommend to join it so that you can publicize your work. You can have discussions with other researchers, and you can generally, get information. And I would like to thank all the collaborators I had over the last few years. I greatly enjoyed working with all of them, and it's really my honor and pleasure. All of this work would have not been possible without their help and hard work. And in particular, I would like to thank my partner in crime on tactile sensing, which is Michael Ambetta. I love work with him. He's really amazing. So to conclude, I hope that today I convince you, or at least I show you the direction of how touch is a key sensor modality in both humans and robots. And throughout the last few years, we have been trying to create this ecosystem that hopefully can help the community to accelerate research into tactile sensing. And some of the key parts of this ecosystem include the tactile sensor digit, the simulator Tacto, and the touch processing library PyTouch. And we really want to grow and help the community to grow and do more research better, more efficiently. And I think that this should be sort of obvious from the fact that we open source all of our work, and that we're really trying to engage as much as we can with with all the members, both scientific and industry in this field. And my long-term goal is really to try to make touch sensing practical and useful in the real world. 5 years from now, down the line, I want to have every single robot on the planet to be using tactile sensing and to actually benefit from this, because I think that we have this possibility to really push robotics, manipulation, and locomotion more by doing advancements here. Thank you very much for your time. I'm happy to take questions.
Thank you very much, Dr. Calandra. So let's move on to the Q&A session. Firstly, let me introduce some questions I've got in advance. The first one is, since we humans have an extraordinary sense of touch and our skin is soft, so the combination of the software of these touch sensors can give us any advantages. Sorry, please take your time.
I generally like soft robotics. I think soft robotics is a different approach compared to traditional control, where everything is rigid and you need to be very, very, very good at controlling. Somehow soft robotics seems to have this amazing mechanical intelligence, which they can do really cool things really very simply. I think that that mixing touch and soft robotics, the benefit might be less than control compared to traditional hardware, rigid body hardware, simply because in many cases, the mechanical intelligence that soft robots already have essentially don't leave much space from the controlled side to incorporate sensory feedback or to be better at controlling, because the intelligence is sort of already embedded into the hardware, how it's built. However, I'm generally, I would say, should be tried everything. I would love to see tactile sensing everywhere. And I think that a more interesting question is whether we actually need hard traditional robots at all. If we think about manipulation, why do we want to have human hand finger rather than having maybe 5 tentacles? And perhaps this is actually much better in some tasks. So yeah.
Yeah, thank you. And I would like to introduce another one. Do you think touch sensing is a new concept, or is it just a combination of several other sensing, such as temperature, force, and the sound?
So I think that there are several questions actually here. I think that as a community, touch sensing is an old community. It has existed for many decades. I think that the technologies that sort of the community has been using over the years has changed, and certainly we currently use technologies that are from other fields, like vision-based tactile sensors. We use camera that comes from other fields. I don't necessarily think that this is going to be true in the future. I think that technology will advance. I also believe that some of the solutions that the tactile sensing community might converge to might be radically different compared to what other community cares about. If we want to have, for example, touch, we need to have interfaces that ideally are very, very thin, that are very, very robust, and maybe somebody who does computer vision doesn't care about that. So I think that ultimately we will move away as we become more mature as a field. The hardware will converge to something that looks very different. From a processing point of view, I think it's already obvious that although we do use some of the machine learning and computer vision tools, those solutions are not tailored to tactile sensing. And there are specific solutions that can exploit more structure and will have greater benefits.
Thank you so much. Okay, then let's have a question from the audience in person.
Thank you very much. So my question is about the usefulness of the open data set of tactile sensing. So usually the data set is important, especially for vision and audition or something. But tactile sensing depends strongly on the context. How to move the hand or the surface softness or other the property of center. So is it useful for in general, or how to use such data set for the general researchers?
Thanks. This is a deep question. My thoughts, my line of thoughts in this moment is that it's true, certainly, that tactile sensing is an active sense, as you said, and to get the best benefit of the data, you would need to be able to control whatever interaction you have and collect data for that specific interaction. I also think that as a community, if we want to be appealing to machine learning people, machine learning people will not be interested in, for example, having a robot to control, simply because it's too hard for them. So the possibility of having datasets that they can just download and play with, I think will be very important to be, to grow toward those type of community. And it's very likely that there is still very interesting questions that can be answered. Question, for example, surrounding the, what are the structure of the models? In many cases, yes, it will be great if you can collect data, but if you have an offline data set, this is going to be enough to compare different types of models or different types of perhaps even features that you want to learn.
So thank you for the great talk. I think a lot of researchers want tactile sensors and they use tactile sensors, but somehow industry is still more like hesitant to use tactile sensors. They rely on grippers or suction cups, something like that, and maybe recently even soft grippers that you mentioned before. So what do you think needs to happen, but also industry wants to use tactile sensors?
Yeah, that's a good, very, very good question. I think fundamentally we really should try to do things that are not possible otherwise. If you can show that, a hand with tactile sensor can grasp 99.99% of objects that you have at Amazon, I think that this is going to be impressive. This is going to show that, we can do better than just suction cup. If you're able to grasp and at the same time do maybe quality control, measuring dynamic properties of objects, this is also something that, suction cup or soft robots cannot do. So I think it should really be about finding somehow the killer app, sort of that this is something that you cannot do if you don't have tactile sensing. And I think that there needs to be a lot of thoughts. I don't have a specific answer. I can tell you, this is what we should demonstrate. But I think this is the line of thoughts that we have been approaching the problem. And hopefully, we have a couple of ideas that hopefully we'll be able to share in the future over what could potentially be interesting task for the community.
So I think we are running out of time. So I think this would be a last question. Do you have any questions? Okay, then.
I can take two.
Thank you for the talk. So one thing I noticed during the talk was it appears that tactile sense, like touch sense itself, consists of more than one modalities. Like there is force, there is temperature, and there can be vision and other things if we implement in robotics and more our ways. Also, it seems that a lot of researchers with their own approaches have their own preferred modalities to perceive the sense of touch. And I imagine that can be that can cause some problems in benchmarking and producing basically standardizing and benchmarking, producing standard data sets. So from your experience so far, how can we overcome such challenges? Yeah, that's my question.
I'm completely both on the fact that we do need sort of multimodal sensors. I think this is inevitable and it's obvious that we do need that. And I think this is going to be the future. Some of the challenges there are on the hardware side of things. How do we actually create a sensor which is truly multimodal? And personally, I'm sort of tied to vision-based tactile sensors because nowadays, as a technology, they are fairly mature. But this is not a sort of religious vision. If somebody else come and say, hey, we have this new sensor which is multimodal and can do all of these things, I think that this is the future. I think that just the technology evolves over time, and we need to find what's good now, where we can do progress now. But absolutely, there were several talks at IRIS that were also discussing the fact that humans use multiple modes. Vibrations are super important. We know that. I would love to see more of that.
Okay, so the last question would be given by Professor Ogata.
Thank you for a great talk. Actually, it's not question, just a comment related to Mori Sensei's questions. Actually, for people that be all researchers, there's some discussion about tactile senses, kind of sensor fusion with not just a touch, but also in actions, because as you mentioned, it's always caused by the actions. So, for example, case on recently with AI on the language is just purely focus on the language part, but it should be always depends on the context. So it could be embodied based on embodied intelligence. So tactile sensing is kind of similar, something like this. So what kind of context? So this very similar touch, but meaning completely different. So maybe so by combining robotics today, as you mentioned finally, so that is a very interesting approach to finalize how to make such kind of data set or intelligence, tactile-based intelligence, not just recognize object, not just recognize a target. So with how to generate the motion, motion generation is generating tactile senses. Okay. So that is very interesting. So so maybe the question could be do you think about it kind of such a fusion aspects on so tactile sensing actions? So do you have any idea to approach such kind of fusion to sensor?
I think it's really important. I sort of hinted very briefly about the fact that I believe that touch does its best when it's active as a sensor modality. And this activeness comes from the fact that you're able to control it while we are sensing. So even if you think about if you're searching for an object in the dark, you are controlling, you are at the same time deciding where to move the finger to understand the object, to grasp it, to maybe reconstruct its surface. So I think it's very high in the the nature of touch is active, as you said. Yeah.
In that sense, I think tactile is not just a sense, but a base of the intelligence which could generate our motion and behavior. Yes, very interesting. Yeah, thank you.
Okay, I think we are out of time, so let's really finish this. Thank you for your great talk, Dr. Roberto Calandra. Also, thank you for joining our today's talk. And yes, give a big hand to Dr. Roberto Calandra. Thank you.
Thank you for having me.